Welcome, everyone. Welcome. It's good to see everyone joining us. I'm very excited to welcome Jeff Wiener back again on this virtual science camp. As those of you who are here from his previous talk in January will remember, we were all really excited with everything he was saying, and we kept asking him questions, so he stayed on really late. And he got a lot of ideas that he wanted to share in another talk. So he agreed to come back for another talk, this one featuring accelerators and decelerators. Oh, just to mention, as you guys are coming in, please feel free to say hi in the chat, especially if you feel like saying where you're from or anything like that. Please feel welcome and feel free to participate throughout the session, especially using the chat. And once Jeff's talking and once he starts going through things, please feel free to ask questions at any time. Again, with a preference for doing it through the chat so that I can moderate things. I'll find a time when it's appropriate to relay the questions to Jeff. If you feel like being the one to talk, let me know. And if it seems appropriate, we'll let you try and switch on the mic. But most of the time, I'll be reading your questions to Jeff to keep things up like that. Other than being really excited to have Jeff back and to see what he's going to tell us this time, I think that's all I have to say. So now, Jeff, I'm going to turn things over to you. Thanks again for joining us.
Awesome. Well, thank you so much for having me again. I'm also very much looking forward to tonight. And I'm happy that a lot of people are coming back, and I hope a lot of people who joined at least my first session are now back here, because it's really, as you said, the idea is now to go a little bit more in depth into two directions that we discussed at the end of my first presentation, quite in depth. But I think we discussed it makes sense to go a little bit more into detail. I did try, well, not try. I had a lot of fun preparing this talk tonight. I thought I would just, do some standard stuff and at some point end up boring people to death with accelerators and decelerators. And so I thought, no, this time I want to do it. I want to challenge myself. And so the talk tonight, or the presentation, and then especially the discussion, so what we will discuss afterwards, is about accelerators, so particle accelerators, but also particle decelerators, and all of that from a penguin's point of view. And this might sound strange at the beginning, and I promise you at the end, it will make sense why I chose the penguin. So I suggest I will just start directly, and I will also do it a little bit more interactively. So there are a couple of questions that I will ask all the participants throughout my presentation. So you will then be able to choose 1 out of 4 answer options. And of course, this is not a quiz where you will get any, grades or something. This is just so that we all see what we are thinking. And also, especially for me, depending on how people in the room are responding, I will then take a different tour in my presentation. So for every quiz, I have a new way of storytelling. So I will rely on your help. All right. For those of you who either have been with me the first session I took part in this virtual science camp, but especially for those who are new, at least to my session, let me just briefly remind you that I work at CERN, which is a French acronym and stands for the Conseil Européen pour la Recherche Nucléaire, which is in English the European Council for Nuclear Research, or as we call it these days, the European Center for Particle Physics. And back in my first session, I explained that we are an international collaboration, so that there are a lot of member states coming together to support and to keep this organization running. Then I mentioned that education is a really important part of CERN, so that we train the next generation of scientists to do one thing, and this one thing is fundamental research. And we also briefly discussed that out of fundamental research, we always have some new technologies that are first helpful for our research, but then end up in our daily lives. And here, of course, I mentioned the World Wide Web as probably the best outcome of fundamental research, because without that, we would not be able to have this session tonight. And and there are other examples, for example, the touch screen that we also discussed. So that's a cool thing, but of course that's not what we do it. That's not why we do it. We do it to really gain new insights. And that was just a very, very brief, really super brief summary of what CERN is doing or what I discussed in my first session. And now I want to move over and introduce you to my good friend, the Penguin, who is going to join us now throughout this whole presentation. And this Penguin he wants to know a lot of stuff. So he's going to ask questions, and I will, well, read them on behalf of him or her. I don't even know I don't know if it's a he or she. I have no idea. It's a penguin. and now the first question that this penguin is asking us is, which question are we trying to answer at CERN? So this is maybe a couple of, a repetition of my first session, but if you haven't been to my first session, you can still give it a try. So there are 4 answer options. The first one is, where do we come from? The second one is, what are we made of? And the third one is, where are we going? Or the fourth option, all of the above. So Michael, I would now kindly ask you to open the poll so that everyone, if they want, of course, you don't have to feel obliged, but I would be very happy. You can now choose whether it's A, B, C, or D. And we will see what people are answering. Now, I just said we will see. That might be a hint, but we will also see what it could be. Or maybe you have an idea. No, it doesn't work really. But we'll see. Well, I'm having too much fun with this poll. I'm hoping people are answering.
Yeah, we have 14 answers so far. Do you want me to share the results yet?
Yes, please. I don't know how many are in the room, but this is just the first one to see what's happening. Wow. We have a lot of smarty pants in the room. Very good. Exactly what I was hoping for. But of course, this question was really just to double check that the poll is working and that our participants know. I mean, I think by now everyone knows how to operate a Zoom poll. So very good. It is absolutely true. So the majority of you chose number D, all of the above, which is always the simplest answer in such a poll. So just to remind everyone, it is true, all of the above is correct. And just to remind you, so we at CERN, we try to answer the fundamental questions of humankind. That's what we usually like to say. And so the one is really, where do we come from? Where we in science like to explain it by using the Big Bang Theory, not the sitcom, but it's a fun sitcom, so I always like to use that as an example, but it's really the Big Bang Theory that explains that 13.8 billion years ago, everything, the whole universe was created, and everything that we now find within itself was created back then and then developed over time. And we have really no idea how that really worked. I mean, we can work our way back, always closer and closer to the Big Bang, but what happened shortly after the Big Bang, well, we have not really a lot of ideas. So that's a lot of research going on there. Then what are we made of? That is particle physics in itself. So really the fact that everything is made of elementary particles that interact via fundamental interactions, that is particle physics. And we still also have a lot of open questions there. So if you're curious, there can be a Nobel Prize for you waiting. And the third aspect is, where are we going? That's the other side of the universe that is currently expanding like hell. And we don't really know whether this will continue forever or whether it will stop and maybe come back. We don't know. So these 3 questions, these are really what we can, present to all our audience, what we are studying. And of course, in each of those chapters, we have hundreds of different questions that we like to answer. And so when we say we like to answer them or we investigate them, well, where do we do that? We do that at CERN. And also this slide is something that might look familiar to you if you've been to my first session. So this is this beautiful overview of what CERN looks like. So we have a triangular shaped main site right here. This is where we are located if we are on site. At the moment, we are still mostly working from home ourselves. Then we have a second site that is called CERN-Prefseur, just because the small French village around it is called Prefseur. And of course, in the back of the image, far in the back, the big white spot is the Mont Blanc, the highest mountain in continental Europe. And that is always a beautiful sight when the sun goes down and shines onto the Mont Blanc and it turns pink. It's beautiful. I can highly recommend joining us at some point, either working with us or just visiting us once it's possible again. It is beautiful. But the last time I also pointed out that this image, where of course we see a big yellow circle, and it's even it has a description saying LHC 27 kilometers. This is the Large Hadron Collider, the largest accelerator that we in the world currently have. It has a circumference of 27 kilometers. And this is what we are probably most famous for, but it's not our only particle accelerator. No, au contraire. We have a lot of accelerators at CERN. None of which you can see in this image. So I always have to point it out that this LHC, this circle, a lot of people are flying in with the airplanes to Geneva, and then they're looking out the window and trying to see where this big machine is, but you cannot see it because the LHC is really built underground, about 100 to 180 meters underground, just because nobody would ever want to build or construct a building that is 27 kilometers of circumference. That would be just impractical. And also the fact, if you have such a big machine underground, you're shielded from any outside influences such as rain and snow, but also any kinds of particles or radiation that might be around. So that's a big bonus. So as you can tell, on this image, we only added some graphics, but the real image of CERN actually looks like this. And that was also something where I spent quite some time on explaining this beautiful particle accelerator chain, or not explaining it in detail, but I explained that we have this accelerator chain and that we need different accelerators to connect to each other to accelerate particles step by step. And this is also where a lot of questions came up. Some of them I hope I will answer now, or some of the questions I will give to you, or the penguin will give to you. But I think I will still leave a couple of questions open or unanswered. And I'm hoping that at the end of my presentation, you will then bombard me with more questions so we can then answer them directly and specifically tailored to whatever you want to know. So that is my idea. But first of all, when we accelerate particles, what we mean by that is we give them energy. So we increase their energy. And here, the penguin has another question for you. And the question is, what is actually needed to increase the energy of a particle? So if we want to take a particle and we want to accelerate it, we want to give it a lot of energy, what do we need for that? And here, the four answers are either magnetic fields, electric fields, or magnetic fields and electric fields, or the fourth option, something completely different. It's a tricky question, so thank you for opening the poll, fantastic. So now it's up to you. Again, of course, in this case, there is a right and wrong, there are wrong and right answers, but you will not, it's completely anonymous, and you can really just tick whatever you think is correct. And of course, I will then explain why something is correct and the other thing might not be correct. So now it's really just to see what people in the room are thinking. And this will then help me also to, explain certain things. If you, again, continue to give me the correct answer, well, then we can just move on. All right. Yeah, I leave it up to you, Michael, whenever you want to close the poll, whenever you have a good feeling of how many people replied. Then I'm very curious. I'm very curious to see what people think of this question.
Yeah, I think we're about ready to share it now. Replies has slowed down. Oh, that didn't share it yet. Now it should be shared, right?
Wow, absolutely, yes. Very interesting, very interesting. Oh, I'm afraid I was a little bit mean. I was afraid that my answer options might have triggered you, because the correct answer is actually number B. It is true. If we want to increase the energy of a particle, that essentially means we take it from one side and then move it to the other side. That we do with electric fields. We don't need any magnetic fields or anything else for that. All we need is we take a particle, for example, a proton, I choose a proton just because you can buy protons quite easily. That's why we at CERN use a lot of protons, almost only protons, because we can buy them quite easily. No worries, we don't go to the supermarket and say, hello, can I have 5 protons? And they pack them up. No, that's not how it works. But we can buy a bottle of hydrogen gas, because hydrogen is the simplest element in the universe. One atom of hydrogen has 1 proton, and somewhere around there's an electron. That's it. So if we buy a bottle of hydrogen gas, we have a lot of protons and the same amount of electrons. And then all we do is we ionize the hydrogen, which is a very fancy term for kicking away all the electrons. And in doing so, we ionize the hydrogen, meaning we are left with only protons. That's very simple. I mean, simple for, if you have a very advanced laboratory. It's not easy if you want to do it in your kitchen, but I think in terms of physics, it's quite straightforward. So long story short, if we now want to take this proton and increase its energy, so we want to move it from one side to the other, we can use an electric field because the proton itself has an electric charge. It has a positive electric charge. And so if we take the proton here, and then, for example, here is a negative field component, and here is a positive field component, well, then the proton will move in the direction of the negative field component, because plus and minus attract each other. And at the same time, the positive field component will push the proton away further to the negative field. But I can already tell that me doing this with my hands is not really clear. So let me show you a very nice animation of what we do at CERN at the very beginning when we want to accelerate protons. So what you can see here is, wow, nice, a bunch of protons. They are drawn in red, but they don't have a color. We have no idea how they look like. But this bunch of protons is being accelerated in this structure. I think I will just start the animation one more time just to go through it, because you see in red and blue, those colors are changing. This is just our way of representing that the electric field that we use is changing its polarity. So the electric field, so at the moment, what you can see here, there is a bunch of protons. We don't take one, we take a bunch of protons, and this bunch of protons is being attracted by the blue side of this metal piece, and blue in this case means negative. This is just how we decided it. Negative has no color, but we have to show it somehow. And now this red bunch of protons is being attracted by the blue side, but at the same time it's repelled, it's pushed away by the red field component, so by the positive side of the electric field. And that's how we accelerate protons. And I can tell, or at least I think I can sense, that this explanation with the animation is better than me doing this with my hands. But I feel the explanation is still not the best explanation. So let me ask my good friends to explain it a little bit better. And my good friends, of course, are my penguins. So how do we accelerate penguins? Well, in this case, this is just an example, of course, but if we want to accelerate penguins, well, all we need to do is, on the one side, we take some fish, maybe, I don't know, and then the penguins, of course, will run to the fish, and on the other side, we take an ice bear, which is very mean, but it's just an example, and then the electric field in our real physics setting would then be made of fish and a polar bear. And this fish and polar bear field, which is a very strange example, but I think you know what I mean, pushes our penguins from one side to the other. That's how we accelerate particles. But of course, we don't use penguins. That would be really cruel. Don't do that. Instead, we use protons. And instead of fish and a polar bear, we use an electric field. Like, you take a battery, and then you have a plus pole and a minus pole, and the protons are moving in a straight line. Very simple. That's the simplest explanation I could find how we accelerate particles, meaning how we increase their energy. Now, let's return to CERN and have a look at how that looks like at CERN. So I've shown you this beautiful accelerator chain, which looks very confusing, I assume. I mean, there's a lot of information to take in. So I don't want you to get overwhelmed. I don't want you to look at all the stuff and say, oh, there's a lot of science going on. For now, I just want to focus your attention on where the line starts. And actually, I have to be precise. There are two lines that start. We have one line starting here, where it says LINAC 4, whatever that means. I'll explain in a second. And then we have another line here, and this is where LINAC 3 starts. Now, I don't want to make any mysteries out of what I'm telling you, so I will tell you straight ahead. LINAC is an acronym or an abbreviation, and it stands for linear accelerator. And a linear accelerator is really, really simple. I mean, again, it's not easy to build in your kitchen, but to understand it, it's super simple. We have a pipe. Inside of the pipe, we have a vacuum. So we take out all the air and all the dust that's inside there, just so that whatever is traveling inside of this pipe cannot collide or be deflected by stuff that is in there. So we take all the stuff out, we create a so-called vacuum, and then we apply electric fields, and then we put our protons, for example, at the beginning of this pipe, and then the electric fields, they are changing, and whenever they change, they kick our protons a little bit further. They like they're penguins. We show them a little bit of fish, then they move forward, then there's a polar bear, they move even more forward, then another fish, they move forward. It's exactly the same thing. I like this example. Anyway, and that's what is then a long straight line. And the longer we do that, well, the faster, or let's say the more energetic the particles get. And also the same is true for the penguins. They will start running even faster, and that's how we accelerate these objects. In our case, it's protons. And that's exactly what happens right here. So you see, this is where the line starts, and we have a straight line. It's a linear accelerator. Linear stands for straight, linear. And this is how we accelerate particles at the first stage. And the same is true here. So we have another beginning of our accelerator chain, but instead of protons, we accelerate ions. It says here ions. This is just because at CERN, we either accelerate protons or ions. And since you cannot use the same linear accelerator for both types of particles, well, we have two linear accelerators, number 3 and 4. You might be wondering what happened to number 1 and 2. That would be a very good question. It would even be a good question for the penguin to ask, but I will tell you directly. LINAC 1 and 2, they were built quite some time ago already, because as you probably still know, CERN has been founded a long time ago, more than 65 years ago already. And so LINAC 1 and LINAC 2 were built, but then at some point we had to change them because technology just advanced and we had just better knowledge of how to build even more powerful linear accelerators. And that's why we now continued with number 3 and 4. And as you can see, number 4 from my screen was only installed last year. So it's quite brand new and quite fresh. And we are only now starting to play with it for the first time. So it's quite exciting for us. Even in the pandemic, we are able to operate, or at least now slowly restart our accelerators. All right. That is quite nice. I mean, quite nice. I don't know. I like accelerators. So for me, I could, spend hours talking about this screen, but I don't want to do that. Then this Tuesday evening would at some point, get very boring. Instead, I'm hoping, or I have a feeling that you might be wondering by now, I'm talking so much about linear accelerators, about, accelerating particles in a straight line. And linear. And I mentioned linear so many times. And then I'm showing you this slide at the moment where almost nothing is linear. Almost everything you see on my slides, every single accelerator is circular. So, I mean, something doesn't work, right? Or probably you're guessing that this is my plan. I'm sorry, it is really my plan. And so let me ask our friend the penguin to ask another question to get going. And the question is, what is needed to force particles on a circular path? So we now discussed that we accelerate particles with electric fields, and then they fly or they travel in a straight direction. But how do we now accelerate them, or how do we force them onto a circular path? That's now the new question. And so I'm not a very, creative person. So I just took exactly the same answer options. So it's either A, magnetic fields, or B, electric fields, or C, magnetic and electric fields, or D, something completely different. I'm very curious to see what you think is the correct answer. I would drink a sip of water and eagerly await your answers.
There's an interesting spread of results here.
Okay. I'm hoping what I'm telling you makes sense, and I'm hoping that everyone in the room appreciates or finds it interesting that I also explained with penguins. If this is confusing you, please drop down in the chat and say I'm lost, I have no idea. Then I will try to be a little bit more accurate.
One thing that's confusing me, but it doesn't hurt the example at all. Is there anywhere where penguins and polar bears live together?
That is not relevant. I didn't think this example through completely. I made up polar bears and fish at the moment. So let's not focus on the mistakes I make. Let's focus on the poll.
It's a biology question anyways, not a physics question.
That is true.
It's the poll. And my other question, I'm wondering, with the analogy, what would be analogous for magnets?
Don't ask me this question now. You're ruining my talk. Stop asking the question.
Okay,
where are the results of the poll? Where are the results? Have you shared the results?
Sorry, I meant to share it. Yeah, I could see the results. I thought you could. Okay, sorry. Yeah.
Yeah, because without knowing what our audience answers, it makes no sense to talk about magnets. Okay, so we see that about 50% of all who answered the options, the poll, say magnetic fields. Then we have a spread of electric fields, magnetic and electric fields, and something completely different. Okay, so the majority does say magnetic fields, and I'm happy to report that this is indeed the correct answer. So you can see I was a little bit mean there again, those two questions, but it's something that we at CERN consider to be so important. And I'm so happy that a lot of you got that right now. And I'm hoping that for those of you who did not select the correct answer at the beginning, that this now makes sense to you, what I will explain to you. So there's a big distinction. First of all, if we want to accelerate particles, if we want to increase the energy of particles, we can only use electric fields. That's always true. If we want to force particles on a circular path, which usually is also called, accelerating them because we change their direction. So that's where language gets a little bit in the way of physics. But if we separate those two, it makes absolutely sense. Then we need magnetic fields. And I'm not sure if you've heard of this one here. This one is the most important thing at CERN. It's the so-called right-hand rule, or depending on where you're from, you might know it as Lorentz force, or you might even, in the UK setting, you might know it as one of the two Fleming's rules, because they also use it with left and right. It gets super confusing, and I don't want to go into detail there, because all of those descriptions describe the exactly same phenomena, the exactly same thing. It's just that different parts of the world call different things differently. That's where the confusion comes from. For this talk, for now, I don't want to confuse anyone. So let me just explain to you that this, what we have on my screen now, is a gift of nature. This is something that we found. It's not something we invented. This is just something that nature arranged for us. And we just happen to have the nice hand symbol for it. So what we see here is we use our right hand in this case, and we spread out our fingers in such a way that all of the fingers are perpendicular to it. So there is a 90-degree angle between those two fingers. There is, oh my goodness me, Zoom is killing me. I'm very bad in that. I'm sorry. I tried to turn my hand. Okay, it's the same angle, I think. You get the idea, right? All of the fingers have a 90-degree angle between all of them. I'm very bad at that. I'm sorry. And what we now have is, if the particles are traveling in the direction of my thumb, right, as we see it on my screen. So you see on the thumb, there is a green arrow, and there is a very fancy term saying V with an arrow on top of it. This is just a very fancy way of scientists to say that this has to do with something that is moving. It stands for velocity, but we don't focus on that too much, especially not on the arrow on top of it. We don't, I mean, we can, but it's not the focus now. So the particle is moving in the direction of my thumb, right? Now, there is the index finger, pointing finger, which in the image says B. B is another very strange name for the magnetic field. Don't ask, I mean, you can ask me why, but it's not important now. The magnetic field is abbreviated with a B. Okay, so there is a magnetic field. If we have a magnetic field, and we all know a standard magnetic field as we know it from school, we have magnets, they have a north pole and a south pole, right? That's how we usually know them. There are more complicated magnetic fields, but the simplest way is this north and south pole. So if we have the north pole on the one side and the south pole on the other side, and there is a particle moving through it, then there is automatically a force onto this particle if it has an electric charge. I hope I mentioned that. If not, so we are only talking about electrically charged particles like our proton, for example. So the proton moves straight ahead, but if it moves through a magnetic field, there is automatically a force onto the particle that moves it to the side. And that is exactly what this perpendicular hand sign is supposed to show you, that if the particle moves in this way and there's a magnetic field, then the force goes in this way, for example, if I hold my hand like this. And the only message that I want to get across is if we have the protons that we accelerate with electric fields, right? And they move in a straight line, and we want to move them around a circular path, then all we have to do is construct magnetic fields in such a way that the particles are moving through the magnetic field, and automatically nature gives us then a force that pushes the particles around the corner. That's all we do. I mean, we don't do anything. We just install magnetic fields, and the particles are automatically then pushed on a circular path. This here, I have to point that out, this sign, right? This is so important at CERN, because without that, at CERN, nothing would work. I mean, I showed you all our accelerators, except for the very first linear accelerators, where we have 2, but everything else are circular accelerators. And that's why this sign is so important. And that's why this, and I'm only going to tell you now, so everyone who's in the room, you know, this is a secret. It's the secret CERN hand sign, or the secret CERN sign, right? So whenever you go to CERN and you want to show that you know your stuff, that you know that you belong, you can just very secretively show some CERN scientists, the secret CERN hand sign, and then they will do the same, and then you know that you know what we know. If they don't show you the sign, then they have not listened to my talk. Then tell them and make it more famous. But this is really the most important thing at CERN, or in physics in general. You see a lot of people who always walk around like this, because we in science, we always try to imagine, okay, what does that mean? What is the force here? That's what we do. Okay. I think I spent a lot of time on explaining that. I want to make it a little bit easier. So by that, let's ask our friend the penguin one more time to ask one more question. I promise you, at some point I will stop asking questions. There are only 5 of them or so in the whole talk, but I do want to give you some questions to think through, because as I've shown you earlier, we don't accelerate particles individually. We don't take one proton and then just play with it. No. We take a full bunch of protons. But I'm assuming most, if not all of you already know that if those are all the same particles and they all have the same electric charge, so they all are positively charged, and all of that is true, if we want to squeeze them together in a bunch, they don't like that. And I am assuming you all know that, because particles of the same electric charge, they really, really don't like to stay next to each other. They repel each other. They really push each other away. And this is not something we can switch off. They always push each other away. But for us in our accelerators, we really have to make sure to squeeze them together. We want to squeeze them together. And so here, my friend the penguin has another question. The question is, what is needed to squeeze particles into bunches? So how can we squeeze the particles together while accelerating them and while steering them around the corner? So what do we need for that? The answers are, as you probably know by now, I'm not very creative. The answers are, again, magnetic fields, or B, electric fields, or C, magnetic and electric fields, or D, something completely different. And the poll is already open. So this is a really tricky question. I mean, all of the questions so far have been tricky, and some of them maybe even mean. But this one, I think, is the most difficult question. I don't want to confuse you. There is a clear answer to it, but if you don't know the answer, that would be good. So honestly, I'm hoping for a lot of wrong answers, because otherwise, if you all know what I'm talking about, well, then I think we're all wasting our time. So I'm hoping for a lot of wrong answers. But you don't have to select the wrong answer just because I told you now. So take whatever you think is the correct answer.
Although with the spread of results, I think you'll be pleased with a number of wrong answers.
Let's see.
And just before I share the results, I'm wondering, is a cathode ray tube or that kind of technology, like, that's different than how accelerators at CERN work, but they still focus charged particles, right?
They do. That is true.
I'll show the results.
That is true. No, absolutely. Let's see what the results are. I don't think you have shared them. Now you have. Okay. Very good. We have. Okay. Not a lot of people are thinking it's electric fields. I think that is very good. Although what you just pointed out is, of course, we can use electric fields, but it is true. The answer I was hoping for, and so in that sense, not a lot of people are completely wrong. The answer is indeed A, magnetic fields. So those who selected C, that is also correct. But in the context of particle accelerators, it's really only magnetic fields that we use. And I will make that a little bit clearer in a second, especially with a very nice animation that I really like a lot that CERN produced. So I will show you what I mean. So the secret CERN sign, right? It works also like this. So you can have 2 times the force on top of each other. You just need 2 different magnetic fields, and then you can have 2 forces. And if you have a bunch of protons inside, you can just squeeze them together by having them go through a magnetic field that forces them together. Sounds technical. It is technical, but you will see what I mean if I show you this animation. But for this, so here we have a slice of our Large Hadron Collider, and here we have magnetic fields, but they are a little bit more complex because they have. I would just pause the video here for a second. So you see, I'm hoping you can see that it's a little bit small in this animation. You see there's a North Pole here, there's a South Pole here, but there's a North Pole here and the South Pole here. So we have exactly those 2 magnetic fields that we need for our 2 hands. And if we alternate the magnetic fields, the forces that are created, again, by nature, this is just happening because we have the magnetic field, squeezes the particles together. So in this case, you can see this bunch of protons that is traveling here was squeezed together like this. But that, of course, means it spreads out in the horizontal plane. That, I mean, you cannot prevent that. That's why after each of those, we call them focusing magnets, we have another focusing magnet. And now you will see, the South Pole is up here now and the North Pole is here. So it's rotated by 90 degrees. And now let's see what happens with the bunches that go through them. And now we see, instead of squeezing them like this, we squeeze them in this direction, which of course sounds stupid or strange, because if you squeeze them like this, the particles will spread out like this, which is true. That's what they do. But if we always do it like this, if we squeeze them one time like this, once like this, once like this, once like this, then the overall shape of the bunch will always stay together. It will just sometimes look like this and sometimes look like this, but that's okay. And so now we completed all the important information that I wanted to convey to you as to what we need to accelerate particles and to steer particles around. And I found this very nice image of penguins that I like the most, because that's exactly how I think penguins move, not penguins, protons move around in our accelerators. You see, we bunch them together in a nice bunch, like those 3, look at them. I mean, they're super proud of them, right? Oh, no, I love penguins. and we steer them around. Michael, don't ask me for a good analogy now. I think with the fish and the polar bear, I always screwed up a lot. So whatever. Don't worry too much on the analogy. Let's just appreciate how cute penguins are. And I promise you, at the end of this session, it will make sense why we have so many penguins in my presentation. I promise you. But okay, I think we now looked a lot at those penguins. Anyway, okay, sorry. So that's how I imagine them. But now, I think by now, I don't know, 40 minutes in, you're probably asking yourself, why? Why do we accelerate bunches of particles in the first place? I mean, why do I have to listen to this crazy guy? Why is he showing me so many penguins? And I think the penguin agrees with you, because he also, or she also asked the question, why do we accelerate bunches of particles? So what do we do with them? What is it that we do at CERN with accelerated bunches? This is really now a fun question. The question is, A, to study those accelerated particles, or B, to collide them with each other, or C, to smash them into the wall, why not? Or D, to get rid of them. We accelerate particles to get rid of them. Those are the 4 options that you have. And I think it's the last, or one of the last quizzes, so I hope you enjoy that. This is really not, it's not a trick question, it's just a very tricky question, but I'm really curious to see what you think, or what you would do with accelerated particles, or bunches of particles. I'm very curious.
And maybe we'll give it another 5 or 10 seconds. We've got a number of responses already.
Sure.
Okay, and I'll close the poll and share the results.
Wow, very interesting, very interesting. Okay, very interesting. Okay, so it is true, the majority of you got it right. Here, to be honest, I was a little bit mean. The correct answer, there are actually 2. There are 2 correct answers if you want. So for all of you who answered number A, to study them, that was, I think, the trickiest answer option here, because of course we accelerate particles to study them, but we don't study the particles that we accelerate directly. That's not what we do. What we really do is either we collide the accelerated particles with each other, and then in those collisions, new particles are created, and those are the particles that we study and that we investigate. So that is true. Or what we also do is to smash them into the wall. That was a little bit, I just wrote that easily. Of course, we don't smash it into a wall. We smash it into a metal piece, for example, a target, because then the same thing happens. They collide with this metal piece, and also new particles are created, but it's a different process. So we also do that. But we are most famous or most focused on colliding them with each other. But we also do answer option C. So if you selected that, it's correct. Whoever answered number D, I have to disappoint you. That is really not why we do it. That would be a waste of time and money and energy and everything, that we just accelerate them to get rid of them. No, that's not why we do it. But I'm happy you selected it, because I thought very hard of what to add as an option. So thank you so much. But now I really want to show you what it means to collide them, because 2 options are correct: to collide them with each other and to smash them into the wall. Both answers I will still discuss today, but I know that I'm already, as usual, running late. So I will definitely come back to that. But now I will only focus on answer number B. Okay, so we only now look at the colliding aspect. But I will come back to the other aspect in 2 more slides. So here I have this awesome animation. This is probably my most favorite animation that we have at CERN, because it really shows you what happens inside of our huge particle detectors. We have those bunches. So each of those orange, clouds is bunches of protons, billions of protons, nicely packed together, and we collide them. So I will just stop the video here for just 1 second. So we collide them, meaning we cross their paths in the inside of one of 4 really, really big particle detectors. I mean, those detectors, I told you in my first session, they are huge, 26 meters high, 46 meters long. It's incredible. It's really huge. And those bunches, we separate them by about 7.5 meters. So 7.5 meters, they are spread out, but they are moving quite fast. Yes, they are moving with almost the speed of light. So for them, the separation of 7.5 meters is not a lot. You will see in a second what I mean. But what happens in each of those bunch crossings, so those bunches cross, and then some of the particles collide, and they create new particles. So that's what we see, this this sphere of particles that moves out from the center of the collision point. That's what happens every time we cross the bunches. But now you're probably asking, okay, how often does that really happen? Well, let me show you. So as I said, they are separated 7.5 meters, but since they're moving so fast, incredibly fast, this time is only 25 nanoseconds. Can you imagine? 25 nanoseconds. So what we see here is a really slowed down process of something that I cannot imagine. This is really, for me, this is too difficult to imagine how that is in real world, but that's exactly what happens. Every 25 nanoseconds, we have a bunch crossing, and then hundreds, if not thousands of new particles are created and move out, and those particle detectors detect all of them and measure their properties. And after 25 nanoseconds, they have to do it again and again and again and again, and that continues for hours. I mean, this is the most mind-blowing aspect we have at CERN, to me at least, how often we collide the particles, just so we get a lot of data. We need a lot of statistics for our research. And this animation, I think, is really explaining it in nice detail what happens inside of those collisions and why we do it. Because in the collisions, new particles are created, and these are the particles that we want to investigate. Some of them are completely known to us, or I mean, all of them are known to us, but we are hoping that in those collisions also new particles are created that we haven't found yet, that we haven't seen yet. So far, that hasn't happened after we found the Higgs boson, which was the last really new particle to us, and that was already quite some years ago. But we are hoping for new particles to be created in those collisions. And since this is very, very rare, we have to do it a lot of times per nanosecond. So this is really the process. So if you are now overwhelmed by all those large numbers that I just told you, or by the short times, I can assure you in the penguin world, collisions are a little bit nicer to see. So I brought a penguin collision with me just to we see boom. I'm sorry, I found it and I found it funny. So that's how, in the collision. So this is a bunch crossing, right? So each penguin is a bunch of protons, and we don't have collisions head on. We collide them. I like this, but okay, it's, again, this is just an example. We all know, physics is not it's not as funny as those penguins are colliding. Anyway, okay. I'm moving on because I'm running out of time, and I haven't even talked about decelerators, and that's also what the penguin is asking me now. What about decelerators? Because so far we only discussed acceleration, right? We accelerate particles, we give them more energy, so that we then collide them and create new particles. But we also discussed decelerators. So the question from the penguin is a really good one. What about decelerators? And here I brought with me an image of where we at CERN need decelerators, because it is true, at CERN we have a lot of accelerators, that we have the strongest and most powerful accelerator in the world, but we also have the best decelerator. So a particle decelerator is a machine that decelerates particles. So it decreases their energy, it slows them down. Very strange. Why do we need that? I will show you. We need it right here at CERN. At CERN, we have an awesome place. It's called the Antimatter Factory. And this is absolutely true. It is a factory for antimatter. Now, before we discuss anything about decelerators and anything, whatever that has to do with the Antimatter Factory, I want to briefly clarify words, because words are always the things that get us into troubles, and people use words for completely different reasons, and then we are super confused, and I really don't want to confuse anyone. So let me briefly show you before we discuss the Antimatter Factory. And of course, for all of you who joined the virtual visit to the Antimatter Factory in the previous science camp, you already know what's happening, but I will just still clarify that. So on these slides here, what I brought with me is a distinction between matter and antimatter, because people are using different terms for different things, and I always like to clarify as much as possible. So I remember, I hope you remember, I talked about hydrogen, right? The simplest element in the whole universe. That's the easiest atom that we can find, because the atom, as we describe it, is contains or is made of one proton, and somewhere around is an electron. And I've illustrated that on my slides, but I tried to do it in a way that you cannot really see it because we don't know how atoms look like. So whatever I put on my slides is wrong, or it's it's just a model or a way of describing it. So I decided I just make very light slides that you might not even be able to see because we don't know how atoms look like. But if you can see that here, so there's a small p under the hydrogen heading. So this is the proton that is, somewhere in the center if you want, and then somewhere around in the area that we like to call the orbital, right? This is just a name tag for the area around it. Somewhere there, we don't know where, is an electron. I just decided to put a small e for the electron here because in this case, if you look there, well, it happened to be there, but it can be anywhere in this area. So this is how we in science describe atoms, at least in this easy stage. So an atom, a hydrogen atom, is really just a proton, and somewhere around is the electron. Now this atom, or a lot of those atoms, can make up matter. Matter is everything that we can touch. This is usually the best description that we use. Whatever we can touch, so it can be, the table or us ourselves, or even the air around us or water. All of that we can touch. All of that is made of matter. And matter itself is made of particles. For example, hydrogen is what we call when there's a proton and an electron. So obviously, what is then antimatter, or what is, let's start with antihydrogen. Well, antihydrogen is exactly the same thing. It's an atom, but in this case, it's an anti-atom because it is made of antiparticles. And this is the big difference, because antiparticles, so in this case for the antihydrogen, you see here another P, but I put a line, a bar on top of it. This is just our way of symboling that it's an antiproton. So we have the antiproton here. And then somewhere around is the anti-electron that you might know we also call the positron. But then again, this is just a name tag. It doesn't matter how you call it, as long as we know that it's the antiparticle of the electron. So an antiproton and an anti-electron, they together make antihydrogen. That's what we like to call it. And this then, a lot of antihydrogen atoms together could create, or could be considered, antimatter, because it's a lot of stuff that is made of antiparticles. But it's not just antiparticles alone. They are all bound together, for example, in the atom of the antihydrogen. But you see, my language now switched to a completely probably, I don't know, state, because there is no antimatter in the universe, or at least we don't see it anywhere in the universe that there is antimatter. We see antiparticles, but we don't see them combining into anti-atoms, antimatter, etc. Except for one place. There's one place in the whole universe that we are 100% sure that there is antimatter, and this place is CERN's antimatter factory, because we created artificially, we created on our own. That's what we do. So for that, no worries. We don't create, anti-iPhones or anti-cars or so. No, that's too advanced. We really go for the anti-hydrogen, because you have to start with the simplest element, and this is the anti-version of the hydrogen. And for that, we need antiprotons and anti-electrons. So this factory that creates antihydrogen needs two ingredients, the antiprotons and the anti-electrons. Now, where is this antimatter factory located? So you see here again this big accelerator chain where I talked about accelerators, accelerators, accelerators. Well, not all of those circular shaped objects are accelerators, because right here where you can see A, D, and Elena, these are the names of two decelerators. So this is our antimatter factory, because in the antimatter factory, we don't accelerate particles, we decelerate particles. Why? Well, if we want to build antihydrogen, we cannot use, high energetic particles. We cannot take a very high energetic antiproton and a very high energetic anti-electron. No. If we want to combine them into a bound state, they have to be as low energetic as possible. Otherwise, they will never combine into an atom, or into an anti-atom, to be precise. So we have to slow them down. We have to decrease their energy, and then we can combine them, and then we can trap them. And that's exactly what we do in our antimatter factory. So for those of you who have been on the visit, this will now well, I'm not sure if this looks familiar, probably not, because the visit was way more awesome and you've seen the real deal, but that's the plan of the area that you visited during this virtual visit. So what we have is two decelerators. One of them is called AD, which is a very, very strange name. I mean, AD, what does it stand for? It's a very good name. It stands for antiproton decelerator. And that's exactly what it is. It's a decelerator for antiprotons. And so the story, and I don't want to go into detail, I can go into detail, but I know that I'm completely running out of time, so I will now cut it short. But if there are questions, I will be more than happy to answer them. But and I'm hoping I haven't lost you yet. I noticed that I'm jumping a little bit. As you know, we accelerate particles, so now it's acceleration, to either collide the particles or to shoot the particles against the wall. That's what we discussed a little bit earlier. And that's exactly what we do here. So you see there's a beamline coming in here. This is where accelerated protons come in, but then they hit a target. And then in this collision, antiprotons are created, because we have to create the antiprotons in this way. We cannot go to a supermarket and say, hello, we would like to buy antiprotons, because we can do that with protons. We can buy hydrogen, but we cannot buy antihydrogen. We have to make it our own. And so that's why we also have to make the ingredients on our own. So we create the antiprotons, but then when we create them, they have way too much energy. They're way too high, well, too accelerated. So we have to decelerate them. And for that, we send them into this circular machine. So they go all the way around in this big, what we call AD, the antiproton decelerator. All right, now I'm going to do a mean thing. I've told you a lot of stuff. It was confusing, and now I will confuse you even more, because now the penguin again has another question. Because the question is, what is needed to decrease the energy of particles? So how do we do that? How do we decrease particles, knowing that we do it in a circular machine and we want to decrease their energy, right? So this is the trickiest questions of all the questions. It's also the last question, I promise you. So what is needed to decrease the energy of a particle? Is it A, magnetic fields, B, electric fields, C, magnetic and electric fields, or D, something completely different? It's the last poll, I promise you, and I will be done in 1 minute or 2 minutes. And then it's 7. This is now really the meanest question of all of them. This is, it's difficult. It's really tough. It's really tough. But then again, it's 1 out of 4. So even if you guess 4 times out of, if you guess 4 times, you will be right once, on average.
And we've got a bunch of results, so I'll close the poll in another couple seconds and then share the results.
Nice.
Okay, and that extra seconds helped. It actually let 3 more results come in, so it's a good thing I waited.
Okay. So
so
wow. Oh my goodness me, I'm very happy. I'm so happy, because this question, the majority of you did say B, electric fields, and that was really the answer I was hoping for, because it's correct. But it was a trick question, so I hope I did not mislead too many people who selected magnetic fields or even C, magnetic and electric fields. Because as we discussed earlier, to increase the energy or to decrease the energy, all we need is electric fields. We just need to switch on the electric field in the right way. But the magnetic fields don't play a role in the energy increasing or decreasing of particles, not at all. We do need them, of course, if we want to keep them on a circular path. But for the question here, that was really mean, because I showed you a circular machine and then I asked this question. I'm a mean guy, I'm sorry. But the idea is really that I want to get across, and I'm hoping I got it across and I didn't confuse you too much. With electric fields, we can increase or decrease the energy of particles. And with magnetic fields, with our secret CERN handshake, we can move the particles around in circles. But it doesn't matter if we increase or decrease the particles, they can still go in circles. We just need the magnetic fields. And of course, with our friends, the penguins, the decrease that would then mean that instead of, pushing them to the fish, we just put a polar bear in their way, and then they will be like, oh, no, I will not go fast there, I will slow down. But I think we established that this analogy is really not a good one. So let's appreciate that penguins are super cute, but we should probably also discuss, to bring it to an end, at CERN, this is the only place where we know for sure that there is antimatter. Of course, we are assuming that somewhere in the universe there has to be antimatter out there, because we know antiparticles exist. So it would be very unlikely that those antiparticles do not combine and create antimatter. Unfortunately, as far as we can see, there is nothing out there. So we at CERN created artificially to investigate it. So we want to figure out what is so special. Why is nature preferring matter over antimatter? Because from our, particle perspective, there is no difference. I mean, they're made of particles and antimatter is made of antiparticles. But aside from this, we don't really understand why there is this difference. So that's why we investigated. And now I'm coming to an end with probably the question you're all wondering a lot. What about all these penguins? Why did I choose penguins? Why? Well, there were good question. There were two answers for that, and with that I will finish this session. The first one is the advanced version, because there is something that is called the penguin diagram. I don't know if any one of you has seen this already before. It's clearly not easy physics. This is really, really advanced physics. That's why we have one of our most famous and smartest theoretical physicists. His name is John Ellis, and he's brilliant. I like this guy. He's so fantastic. And he came up with this kind of diagram that, as you can see, kind of looks like a penguin. And you're probably wondering, okay, but why is this really smart guy? Because this is really, he is the theoretical physicist, if you want. Why does this guy draw a penguin diagram? And the answer is, he lost a bet. I'm not kidding. He lost the bet. He went to a bar, he played darts with some of his colleagues and the student, and then at some point, when playing darts, he lost the bet, and then he had to include the word penguin into one of his papers. That was the bet. I'm not kidding. I'm not making this up. And he, of course, he was not one who says, yeah, okay, I would just, sneak in the word penguin somewhere. No. He thought, okay, how do we make that properly? And he took this diagram that you now see on this blackboard, and he turned it a little bit around and tweaked it. So the physics is still correct, but it also looks like a diagram. It also looks like a penguin. And so that's why the penguin diagram is very famous. And the reason why I chose penguins is, this diagram has to do with the difference between matter and antimatter. I don't want to go into detail there, because this is really tough physics, but for everyone who is curious to find out more about that, all you have to do is Google penguin diagrams, and then you find a lot of papers that you can then enjoy and read and hopefully understand. If you understand them, come back to me and explain them to me. They're really tough. But the official reason why I chose penguins is, I like penguins. But why do I like penguins? Because penguins are curious. Penguins are really curious animals. And you see that here. Look at this penguin. He's super curious. I mean, he's investigating. He's trying to figure out what's going on here. Oh, okay. This is difficult. So he's curious. And I can relate to that so much. And this is what I want to finish this session now. Curiosity is what we need everywhere in the world. I mean, not just in science, but especially in science. We need curious people. We need people who want to figure things out, who want to explain things. And so that's why curiosity, I think, is the most important quality if you want to become a scientist, or if you want to study something scientifically. So curiosity, but it's not just in science. I think we can all agree, the people who are most interesting to us are the people who are curious. And so that's what I think we can all learn and take away from penguins, like this guy. And pay attention when he loses the soap bubble, because at some point he loses it. He's really angry. He's like, what? It's the last split second. Anyway, I like penguins. Okay, on this note, thank you so much for paying attention. I hope you enjoyed that, but I'm hoping even more that you now have a lot of questions that we can still answer. I think we can stay a little bit longer, a couple of minutes, to go through any of your questions you may have. And thank you so much for your attention.
So Adrian's asking, are there any known uses for antimatter?
Ah, very good. Very good question. No, it's the very short answer. So for antimatter in itself, we don't have any application. The reason for that is it is incredibly difficult to create antimatter. And again, we are talking about anti-hydrogen. We are not talking about, awesome physical stuff. No, anti-hydrogen. And so it's a lot of work to create it. And it's even more difficult to store it, because obviously matter and antimatter, they must not touch. I mean, if they combine, or if they come close, they annihilate. So they cancel each other out, and we see a lot of radiation, so a lot of photons or set bosons going out. That's what we see. So that's why if we want to study them, we have to suspend them into really clever configurations of electric and magnetic fields, so in those traps. And that's why it's a lot of work to already investigate them, let alone using it in some way. So we don't know of any applications in that sense. A lot of people ask us if we can use them to, power our spaceships. If we take a lot of antimatter and then we have it annihilate with matter, and that generates so much energy that it pushes the spaceship away. The problem is, conservation of energy is always there. So no matter how much energy you put into creating the antimatter, you will not get more out of it. And so that's why there's no use that we can think of at the moment. No. But you can never say never. But here I would be quite skeptical if we would ever be able to see antimatter being used in our daily lives. Okay.
Okay, and then there's a question, can we transform a particle into its antiparticle using a Lorentz transformation?
Wow, that is a very good question. That is a very, very good question. Not directly. So a particle cannot change into its own antiparticle. That is not possible. The reason for that is conservation of any quantity that you want. So charge conservation, any conservation of any charge. But what can happen, and that's what we do at CERN. So that's why I like this question for so many reasons. It's so smart, but it's also helping me to explain one more thing that I did during my presentation. When we smash the protons into the target, right? So not against each other, but this is a metal piece made out of iridium, which is a certain type of material. In these collisions, the proton collide, and in those collisions, the energy of the proton transforms into antiprotons. But that does not mean that the proton in itself changes into the antiproton. That is not possible. But as we might know, or some of us might know, the proton is made of quarks and gluons. It's not a point-like object. It's a composite particle system. And so the quarks and the gluons, they all carry a certain amount of energy, and this energy can then transform into creating an antiproton. But to be precise, this is not a direct process. But so if you want, officially, no, we cannot transform a particle into its antiparticle, but unofficially or in our experimental settings via some detour, we can.
And to add a slight question to that, there would also be a creation of an electron, or no, a positron. There would be creation of another particle that still conserves charge.
Exactly.
Case, right?
You would still have protons coming out, of course. Yeah. So that's Thank you for pointing that out. I was not precise. If you smash a certain number of protons into the wall, this certain number overall has a certain number of charges, and at the end, after this collision process, the same amount of charges have to be conserved. So for every antiproton that is created, there has to be also a proton in addition that is being created. Otherwise, the universe would not be happy. And this is not our doing. The universe just gives us a lot of gifts, like the secret CERN hand sign, but also the conservation laws that make our lives just a little bit easier.
And now I get to group a couple questions together because there are two that seem similar. So Martha's asking why we decelerate antimatter and not matter. And that seems similar. Oh, now that I reread it, maybe it's not too as similar, but I'll mention both. Rachel asked, why do we produce antimatter?
Okay.
So it's not why do we decelerate it, but
very good.
Yeah.
Very good. Let me first, so both questions, very good questions, and I'm very happy to answer them. Let me just first clarify, we do not decelerate antimatter. That's not what we do. What we do is we decelerate antiparticles, so the antiproton, to create antimatter. So antimatter is really just, we can only talk about antimatter the moment we combine antiparticles with other antiparticles to create, for example, antihydrogen. I know this is not, a lot of people use the words exclusively or interchangeably. That's why I'm always trying to point it out from the very beginning. So we decelerate antiprotons in this case to then merge them with the anti-electron, and that bound state then we call or is antihydrogen. And the reason why we do that is we want to measure its properties. So we want to investigate if, and if so, what are the differences between a hydrogen atom and an antihydrogen atom? Because in terms of the physics that we know, there should not be any differences. And we haven't found any differences so far. But the fact that only hydrogen exists in our universe and antihydrogen does not exist, there has to be something. Something is off, and we haven't found out yet. And that's why we have to artificially create antimatter to investigate it. That's the reason why we do it. And to answer the first question a little bit properly, or more properly, the reason why we don't decelerate, normal particles like protons is we don't need to create artificial matter. I mean, if we want to investigate hydrogen, we can just, take hydrogen out of the air. I mean, we breathe in and out hydrogen to some extent, or it's in the water, for example. So it's already there. So our world is made of matter, so we don't have to create it artificially. But antimatter is nowhere to be found. That's why we have to create it artificially. I hope that now clarifies those two questions.
And slight exception to that would be isolde, right?
Sorry, what?
Isolde, isn't that the experiment where they're making different isotopes? So they're actually decelerating matter, but that's a very specific exception to that answer.
But they are not decelerating it necessarily. They are just using low energetic. They're using low energetic particle beams in the first place, so that they're
and it stays on the target.
So when they hit the target, so isolde, just for everyone, I think we should clarify that, is another research place at CERN, really cool, one of the oldest research places at CERN, where we shoot a rather low energetic proton beam against the target, and then we create different kinds of particles, because depending on the energy that the protons have in the beginning, the products in these collisions then vary, and also depending on the material of this target. And then we can distribute those different particle beams to the different experimental settings. And of course, I mean, there is some steering and maybe also slowing down or decreasing involved, but it's not necessarily, it's not we would not show it off as a decelerator. Yeah.
Okay. So that shows stuff that I get reasonably wrong as well. So no participants worry about when you have things slightly wrong and you want to ask something, because that happens to the best of us.
Oh, absolutely. Oh, I'm the best example for that. I get so many things wrong. This thing is recorded. A lot of people will tell me what I told wrong today. No worries. Okay.
And there's one that's more of a comment. I think it was an answer to the question why we decelerate antimatter, but I think you'll really like it because it talks about medical applications. And for those of you who don't know, Jeff has recently, have you finished your thesis on?
Yeah.
Okay. I've done a thesis on medical applications for, I'm not getting the right wording of it, like
low and middle income countries.
Exactly. The wording on that,
yeah.
But so this one is saying in reference to why we decelerate antimatter. I think it's because it's useful for cancer therapy instead of hadron therapy.
Very good point. Very good point. And I would be so happy if I could agree, because it is true. We investigated, but again, we did not investigate antimatter. This is only antiparticles. So I really want to focus that we use the terms correctly. So in this case, we would talk about antiprotons. And it is true, we investigated if we can use them for a so-called radiation therapy. Now, I don't want to overwhelm everyone, so let me just briefly explain. If a very unlucky person has a tumor, right, which is very bad, and unfortunately, yeah, it happens. So we have to deal with it. And if you want to treat cancer, depending on the cancer, depending on when you detect it, you can either do surgery and just remove it from the body, and then it works. Doesn't work always, unfortunately, because it depends when you detect it. Then the second is chemotherapy, that we probably all know. That's where you essentially take poison and hope that the cancer gets poisoned before the rest of the body gets poisoned, in very simple terms. And then the third option is radiotherapy, where we shoot radiation against the body and try to only target the tumor. So long story short, we have been doing that for a long time, and we are doing it super successfully. In the very beginning, we did it with photons, but photons have the nasty property that they interact with the body or with any matter immediately. So if the tumor is inside your body and you radiate it with photons, you hurt all the healthy tissues on the way to the tumor. So not ideal. So instead, what we currently use are protons. Protons, same as we at CERN, but at lower energy levels. If we were to use the energy levels at CERN, that would not be healthy. That would really, really kill the patient, so we don't do that. But at low energy levels, it is really, really cool that protons, just because they're different type of particles, they go into the matter or into the body, but only a fraction of them interacts. The majority of them just go through, because atoms are almost empty. So they can just go through and they don't interact. And then only a tiny fraction is deposited on the way to the tumor, and the majority really targets the tumor. So that's why this is way more helpful, because it doesn't hurt the overall body too much. Okay, long story short, a couple of years ago, scientists thought, wait a second, why don't we use, instead of the protons, antiprotons? Because as far as we know, except for the charges between a proton and an antiproton, there is no difference. So they also should go into the body. They should also only interact a little bit, and the majority goes through. But if they then collide with the tumor, there is not just a collision that the protons would also do, they would also annihilate, because antiprotons, if they meet protons, they will not just collide, they will also annihilate, right? As we said, they will transform into radiation. So they would, what we like to explain is, it's like a cruise missile, right? Those bombs that you can fly around, and then they fly somewhere, and then you have them explode, which is very mean, don't do that. But it's the idea that we have with antiprotons, that we send them into the body, and then they explode or they annihilate inside of the tumor, and they destroy more compared to the protons. Unfortunately, so we looked at that. Unfortunately, this research has come to an end, and it's not being used because it was too difficult, and also too it was too difficult to manage that the annihilation, the bomb, if you want, that it only harms the tumor and not, more of the body. So that was then at some point stopped. So unfortunately, we don't use that, but it would have been nice. But to be honest, if we use it with protons, that is probably the best we can do at the moment. And this is really, really significantly better than photons. So we are in a good way. Sorry, that was a long answer, but as you said, I wrote a thesis on it, and I'm very, very enthusiastic about it. And I feel like more people should know about it. So thank you for the question. It's a very good question. And I apologize for the long answer.
No, I assumed when it got asked, it'd be something that you'd be happy to go into detail about. There's one that's probably a really short answer from Ladislav. It's, what is the diameter of the space where protons move in the accelerators, to imagine how big it is?
Oh, very good. Oh, thank you for the question. I didn't even go into technical aspects, because as you see, I'm still running out of time, even if I don't do it. The beam pipes in the LHC, let's go for the largest. Well, it's actually a machine I have. I can't do that. It's behind me. The beam pipes where the particles travel, they have like the size of, if you do like your hands like this, so they have a diameter of about 4.5 centimeters. So that's quite large, because the particles themselves are tiny. And the beam pipe completely, so the width is 4.5 centimeters, but of course squeeze the particle bunches together. So we squeeze the bunches together. Normally, so when they're traveling around, they have a diameter, the bunches, of about 60 micrometers, give and take. But before they collide, so before we cross the beams, we squeeze them even further down to about 16 microns, 16 micrometers. So because the more tightly packed they are, the higher the probability for us is that they really collide, right? So that gives you some idea of how large or small everything is.
Excellent, thank you. Then there's a question from Michael. Is there a theory that can explain the masses of particular quarks or leptons in particular generations?
What is the beginning of the question? If there's a theory or?
Yeah, is there a theory that can explain the masses of particular quarks or leptons?
Very good question. And the clear answer is no. It's really not. It's really not. We have no idea. It's a very good question. We by now know how elementary particles acquire their mass, or at least we know how to describe it. That's what the Higgs mechanism, or the Brout-Engler Higgs mechanism tells us. So that is our current best description. But why a certain particle has more mass than another, we have no idea. It's completely unanswered. And we would be really, really grateful if one or some of you could tell us. So if you're curious and you want to figure it out, please figure that out. That would will remove a lot of headache from our side. So we have no idea.
Another question from the same participant: do the parts of a single particle wave function interact with one another?
Very good question. So just to explain for everyone, again, you've seen me illustrating a particle with a P or with an E because we don't know what a particle is, or at least we don't know how it looks like. We can describe it perfectly fine, and we know exactly what we mean by saying a particle, but what it is, we don't know. If we want to measure it, or if we want to observe it, we cannot, pinpoint to a dot or something. No. It's, as this person completely rightly points out, there is a wave function. So there's a probability function around it. So that's how we describe it. Now, if the particles in our cases collide, you would expect that those wave functions interfere with each other, because that's usually how we discuss quantum physics or quantum mechanics, where wave functions interfere. The good or bad news, depending on how you look at it, is that especially in collisions, in our case, those don't play a role at all. The reason for that is that the particles have so much energy. They are really so high energetic that the more energy they have, the more they behave, or they are described really like objects. I mean, again, I'm not saying that these are objects, but the wave function is so irrelevant in that description that there is no interference or any quantum effects in the collision mode, because this collision mode is so high energetic that new particles are created in this collision because the energy transforms, but there is no interference in that sense. At least not to that extent that we usually know it from our high school education when we talk about quantum mechanics, where we talk about low energetic particles. So quantum effects play a huge role in low energetic particles, because then the observation of a particle influences the result. But in our case, the particles have so much energy. If we observe it, doesn't matter. The energy is so high, so large, there is no effect on that, or no measurable effect. Very good question. I'm very enthusiastic about that as well, as about all the questions. I told you after the first session, the quality of the questions here is just so good. Yeah, I'm apologizing for taking so much time. So I think we can come to an end at some point. I don't want to keep anyone longer than in any case foreseen. But if there are one or two last questions, I'm happy to take them.
There's 3 questions, but 2 of them are from the same participant about antimatter. So maybe we'll get those 3 and then we'll finish. So Paul's asking 2 things about antimatter, and I think it's following up from the tour of the antimatter factory last week.
Okay. Cool.
Do antiparticles fall upwards? And can you talk about the targets when making antimatter?
Okay. Good questions, mean questions, but it's only fair I also ask me questions. So antiparticles, as much as we know, or antiparticles like the antiproton protons traveling in the circular anti-proton decelerator, they do interact with gravity. So we have to correct for them, keeping them in the same orbit, because otherwise they would fall to the ground if you want. So antiparticles, as far as we are concerned from the technological side, we have to correct for that. The big question that the person is probably focusing on is whether antimatter, so again, the bound state of antiparticles, if this one is also interacting with gravity. So one of the examples, or one of the research projects that we are doing at the moment is, or that we are getting close to doing, is to take antihydrogen and letting it drop. So we keep it suspended in our magnetic and electric fields, and then we switch it off, and then we see if it drops down or if it falls up. Hydrogen, we already know it falls down, as everything in the gravity field of the Earth. So masses attract each other. But the thing is, no one has done that with antimatter before. The reason for that is no one has antimatter to play with, because we are the only ones to create it on our own. No one else can do that. That's why CERN is such an awesome place. And I still think we should put it on a t-shirt, CERN, the only place where you can play with antimatter or something. But we haven't found it out yet. If you were to ask 100 scientists at CERN, I'm assuming probably not just 99, probably all of them would tell you, yeah, it's falling down. I mean, where else would it fall? But the thing is, we have not measured it yet. We have never done this experiment. It's a very simple experiment, but we haven't done it yet. So we will very soon know, because there are now at the moment 3 experiments, 3 different experimental collaborations working on that within the Antimatter factory. And they will, once we start again, very soon have initial data, and then we will very soon know whether it falls down. Then probably everyone will be like, yeah, we knew that, kind of. If it falls up, a lot of people will get very excited, not just for the physics, but also for a potential Nobel Prize, because that would be really interesting. But we don't know at the moment. So antimatter in gravity, we don't know yet. I forgot the other question. Target. Target. To be honest, I'm not an expert on target physics. For the antimatter factory, I know it's an alloy. There's a lot of iridium in there and copper. So you have this metal piece, you shoot the particles, the protons against the target, and then behind you have a lot of particles, new particles that are created. And for that, you switch on again your secret CERN handshake behind it, because with magnetic fields, you can separate electrically negatively charged particles from electrically positively charged particles. And since we are only interested in the antiprotons, and we know that they have a negative charge because the proton has a positive charge, we don't care about the positively charged particles, and then we only take the negatively charged particles, among which is the antiprotons, among which are the antiprotons, and we take all the antiprotons out. The rest we don't care, and that's how we get them. That's as far as I can explain it, and I'm hoping that this is okay.
And to separate the antiprotons, like from electrons, because there might be electrons created or just around, their significantly different mass would cause them to be accelerated differently by the magnetic field. And like separating that's
careful,
easy, right?
Not accelerated. The magnetic field will not accelerate them.
Well, if an acceleration includes a change of direction,
then yes, but we have to be careful.
Well, like if they're curving around a ring,
exactly.
The electrons would curve much too hard and crash into the inside.
Exactly. So the idea is really simple. After this collision, you have, if you want, you have a wall, and on this wall, whoops, where's my camera? There's my camera. No, I'm lost. Here, there's a wall, and there's one slit. There's one slit, and so all the electrons would fly here. They would not reach the slit because they have a very small mass, but the antiprotons have a mass, and we calculated that their path is exactly so that they go through the slit, and that's how we sort them out. So that only the particles with this mass, or the energy, if you want, that we expect from the antiprotons goes through the slit, and all the other particles will just crash against the wall. That's a very simple but a very elegant explanation of what happens there. And yes, you're completely correct. A circular movement is an accelerated movement, but at CERN, where a lot of people talk about accelerated particles and they mean increased energy, I am the one who is always pointing out that we are really increasing the energy only with electric fields. And we are changing direction with magnetic fields, and sorry.
And some people would consider deceleration and negative acceleration as well.
Exactly.
But we won't worry about semantics. There's one last question. If you're up for answering one last one, and it's about your opinion on medical physics and its realization, because Antonia, who asked the question, is considering studying it at university.
Awesome. It will probably not come as a surprise to you, but if you are interested in that, I can only encourage you to the most. But that's true for anything that anyone is interested in. I think people, if they have the chance to go to university, they should do it if they are interested in it. And if they have the means, and you should study whatever you find interesting. If it is medical applications or medical physics, I think you will, if this is something that interests you, I think you will do a lot of good in this world, because medical physics is really, really important, either if it's on the application side or if it's on the development side. No matter what you want to do or where you will end up doing, you will make a huge contribution to this world, and you will help a lot of people in very, very bad situations, especially tumor patients. So if this is something that you find interesting, I think I would highly support you. Please go there. And it's one of the, I don't know, it's one of the richest fields in the world, not just in terms of money, but especially in terms of physics. There's so much physics in there, and there's also so much to be found out. There's so much to optimize. We can always be better there. It's by no means a dead end. So if you find it interesting, you will have a long career where you can, you can make a lot of people happy and maybe also earn some money. That's always the best combination.
And I think that was an excellent question to end on. There's one small question that's not for you, more for me, and it's if there's a recording of last week's session. So if you're meaning the one with Marco on detectors and making the invisible visible, yes, there's a recording. It's not yet published, just because I needed to check that who's okay with publishing it and treat the video a little bit, but it should be available within a couple days on my YouTube channel. I'll put a link to it there. Hopefully this session that's being recorded with Jeff will be available there soon as well. Again, like usual, once the recording's made, I'll give Jeff a chance to review it, make sure he's okay with it, and we don't make any changes. If I make changes, it'll take some time, but everything that is recorded will be recorded on there. I'll add links to the schedule as well. And just related to the schedule, to give everyone a quick reminder before we finish up, tomorrow there's a visit of the low energy ion ring. It's one that the visits department is letting us experience. We're one of the first groups, if not the very first group. So it's going to be really cool. If you're not signed up, here's a link to the schedule so you can get to the sign up sheet to sign up for that, because it should be really good. There's more visits and more talks coming over the next couple of weeks, including this Saturday, a Pi Day Eve celebration, which is a really obscure holiday, a bit of a diversion from particle physics, but we'll get back to particle physics right at the very end. For anyone who remembers the session on magnification, we ended with a Rutherford experiment where we were trying to model the Rutherford experiment. We'll get to that with the very last experiment on Pi Day. So it's not completely different, but it's relatively different. Hopefully we see you at some of those. I want to thank everyone again for participating. There were people from 10 different countries I counted. 11 countries were signed up, but like looking through the list, checking names, I saw there were people from France, Turkey, Switzerland, Bulgaria, Slovakia, USA, Portugal, Greece, Ireland, and Iran, which is amazing to have a group of only 30 people from that many different places. So thank you for joining us, and especially thank you to Jeff. It's been really amazing having you back on. Big thank you again, Jeff.
Thank you again for the invitation and for having me back again. And thank you, as you said, for all the questions and for taking part. I enjoyed it a lot. And if it was interesting to you, I'm very happy. And yeah, awesome. And yeah. Ooh, there's one last final question. I will answer that and then I will shut up. So because now I also can see the chat. So what happens to particles that get annihilated? Very good question. So if a particle meets its antiparticle, they transform. And so, for example, let's take an electron and a positron. If they meet, they transform, they stop to exist. And instead, for example, two photons are created. So their whole energy gets transformed, and then two new photons are created. That's what happens in annihilation. It's very simple. I mean, I'm not saying that the physics behind it is simple, but that concept is simple. And with that, I think we can close the session. And Thank you so much again for taking part, and take care and stay safe. And as we say these days, as usual, stay positive, but test negative.